كان يفتح المايك يرقع.
Okay, hello everyone.
Hello, Dr. Hazm.
Okay, so okay, let's start. Last time we talked about convolutional neural nets, the concepts, the architecture, the pooling, and there are many issues actually remaining for this topic, but we cannot cover everything. So today we'll cover some architectures which are very famous, and these architectures have changed the landscape of mainly computer vision. And at the end, we'll talk about transfer learning. And if we have time, we're going to talk about sequence processing. But let us start. So most of these slides are from this course in Georgia Tech. Let us review what we did before. Mainly the number of parameters. And as I said last time, it is very important to know the number of parameters of your architecture, because this is what you are going to code. So if you don't know how many parameters you have, you will not be able to write the proper code. So if we assume that our image is of 3 channels and we have the size is h by w, h is the height, w is the width. And let's say that we have many filters. As you can see here, we have n filters. And each filter is of, could be general, k1 by k2. Normally, k1 is equal to k2. So we need to multiply this by 3 and add 1. Why is this one 4? Anyone remember?
For bias.
For the bias, that's right. So we have number of parameters for the n filters. It will be k1 times k2 times 3 plus 1 and multiplied by the number of filters, which is n. So what will happen that we are going to have, let us say that we have 4 filters here. And so the number of parameters will be, applying this equation, will be 112. And the size of the feature maps that are will be produced after applying these filters or these kernels to the image, the height will be h minus k1 plus 1, and the width will be w minus k2 plus 1. So here we are assuming what? We have made some assumptions here. What are these assumptions? If this is a size. Assumptions about what? About the stride and about the padding. So in this case, what is the stride? What is the value of the stride for this one? The stride is 1 and the padding is 0. There is no padding. Okay. And here is the architecture that we talked about last time. That is, we have an image as an input, followed by convolutional layer with nonlinear layer that is right away coming after the convolution. These are the filters, and these are the resulting feature maps. And here is a pooling layer. What is the function of the pooling layer?
It's used to reduce the size of the feature maps.
Yeah, that's to downsample. And then we can follow this with another convolutional layer with nonlinearity. Doesn't have to have a pooling layer after, as you can see here. And then we have a fully connected layer at which we are going to calculate the loss. And this will be used in training. So, so let us move to the architectures that have been introduced over the years. One of the first one that was very successful was called AlexNet. And this is architecture, as you can see it, from the beginning to the end. It was used for the C4 application, image classification. And one of many of the aspects of this net is that they used ReLU as the nonlinear activation. They didn't use sigmoid or hyperbolic tan. They used special, they used normalization layer. They used their own normalization layer. It is not the batch normalization or layer normalization. They introduced their own. For data augmentation, the one that we talked about maybe early last week was that they used PCA. We'll talk about PCA later on. But they augmented the data using PCA-based data augmentation. They used dropout, and they used ensembling. These two are, if you remember, they are very much related, the dropout and ensembling, because dropout is by itself is some sort of ensembling. And this is architecture itself. So we have the input will be an image of 224 by 224 by 3. So we have 3 channels. This is this one. Followed by a convolutional layer of 96. Sorry, the feature maps will be of 96 features. This will be done by 11 by 11, 96 filters with a stride of 4 and no padding. So this is, as if you look at the figure in the paper, you will find that they have 48 and 48. And then they have a stride of 4. The resulting size will be 55 by 55. Followed by a max pooling 3 by 3. So they will reduce the size by 3. At a stride of 2. So we have 3 by 3 filter at a stride of 2. And this is the max pooling. Doesn't show here, but and followed by a normalization layer with the same size, 27 by 27, 96. And followed by another convolutional layer, which is 27 by 27, this one, 96, sorry, 27 by 27, 256, and here is 128, 128. With 5 by 5 filters, and they used the number of filters is 256. Because I have 256 here, and slide is 1 bed 2, followed by a max pooling layer. So I'm not going to talk about to mention the numbers, so since they are here, followed by a normalization layer, followed by 3 convolutional layers without any padding, without any pooling, but it is a stride of 1 and padding of 1. And then at the end, the very last layer, they have a max pooling layer of 3 by 3 and a stride of 2, followed by two fully connected layers for 4096, as you can see here. Another one for 4096, and the last one is a max pooling layer. This one. This was a very successful architecture at the time. Maybe 2012, 2013, something like that. And then came VGGNet, which is larger than AlexNet. Note that the architecture started to get bigger because our hardware, mainly the GPUs, are becoming more successful. So they had, at the time, we had 2 versions of VGG, 16 and 19. 16 layers. This is why it's called 16 and 19 layers. AlexNet has only 8 layers. As you can see here, if you count those, you'll find that we have 8 layers. 1, 2, 3, 4, 5, 6, 7, 8. This is before the fully connected layer. For VGG 60, the first one, VGG 16 has 16 layer, and 19 has 19 layers. So for they moved from 8 layers to 16 or 19 layers in VGGNet. What they have in VGG, that they have only 3 by 3 convolution, and with the stride 1 and padding 1, and the max pooling was 2 by 2, stride 2. So they don't have so many. It is very similar to AlexNet. As you can see, you have convolution, pooling, and so on. Here they have 3 layers of convolution followed by pooling. In every convolutional layer, the size is the same. So this means that they are adding padding in order to keep the size the same. And at the end, they have once again 3 convolutional, 3 fully connected layer. In 19, they just increase the number of layers. The only difference is that instead of, in the last 2 layers, instead of having 3 convolutional layers, they have 4, and here they have 4. So in the image processing competition that was very famous at the time, they managed to in 2013 they managed to drop the error to 11.7%. In the top 5 errors in this competition. And then the year after, 2014, they took it down to 7.3%. And that's why it was very successful. So if you go back to the AlexNet, they have filters like 11 by 11. The first one is 11 by 11, very big. But after that, they have 3 by 3, 5 by 5, 3 by 3, and so on. in VGGNet, they used 3 by 3. That's it. As you can see, if all filters here are 3 by 3 from the beginning to the end. They're all 3 by 3. But they stacked them. So 3 by 3 here, 3 by 3 here, and before the pooling. So the sort of stacking one convolution after the other. So in this case, if they have 3 by 3 filters, then it acts as if you are actually your receptive field will be of 7 by 7 of one convolutional layer. We'll see this next. That if you have layer 3, like here, you have three by 3 convolutional layers. This will be effective to one convolutional layer of receptive field of 7 by 7. How is that? Let us look at here. So here we have the first convolutional layer, second convolutional layer, third convolutional layer. So let us visit this architecture from the beginning. This is our input to the first convolutional layer. So this pixel, not the colors, okay? The colors indicate where the receptive field from the previous layer. So this pixel will be produced by this filter. Or actually its receptive field will be the first 3 by 3 will produce this one, right? And this pixel will be produced by this 3 by 3. Just try to apply the process and you'll find that that's really correct. That this pixel will be produced by this 3 by 3. Now for the first filter, the produced feature map or the pixel of this feature map, which is the same here, will be produced by this orange square in the previous feature map. You can very easily detect that this pixel is produced by this 3 by 3. And this pixel is produced by the other orange square 3 by 3. And finally, in the third layer, this pixel is produced by the red pixel in the previous feature map, this one. Now this pixel, as you can see here, if you try to link it to the input, you find that this pixel is produced by those number of, so you need to cover the receptive field of previous layer. So this pixel has this receptive field, and these 2 pixels, orange pixels, has this receptive field. Actually, this receptive field is here. And these 2 pixels, the purple pixels, will have this receptive field, the blue receptive field, which is 7 by 7. So this pixel in the last one, the red one, is produced by a receptive field of 7 by 7. So you could, one could have said that, so why don't we start at the beginning with a filter with 7 by 7? It has the same effect. So the reason is that you have much deeper and many or 3 nonlinearities. So you are going to extract much more complex features. This is the reason that when you do that, your features will become more complex, much richer. This is one thing. The other thing is that you are going to have fewer parameters. So if this, if you have, here we have three filters, sorry, three convolutional layer times the filter is 3 by 3, right? Times C squared, C is the number of channels per layer. But if it is just one convolutional layer, it will be 7 squared times C squared. So you get less parameters and you get better representation. And this is what made VGG better than AlexNet. And this is the architecture of VGG. As you can see from the beginning, so if you just count up to here, let us count those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19. This is a 19 one. So start with the input, same input, because 224, because these are the size of the training images. So they have to start with 224. So this is a good reason for this value. And of course, time 3, and then we have two convolutional layer. They're all of 3, conv 3, conv 3. Here they not only calculating the number of parameters, but they also calculate the memory, how much memory they will take. Because when you use a GPU, memory is very crucial. So you have to count the number of parameters that you're going to need. Not only the parameters plus the size of the data that you're going to use. So like for the input, you have 224 times 224 times 3. You are going to have, for just one image, you are going to have 150K. For the first convolutional layer, which is 224 to 24, 64. So this is the number of parameters, and this is the size of image. Now for one image, we go from 150K to 3.2 meg. The output of the feature map is the same as the input. This means what? The size of the convolution is the same as the input. This means
maybe it will produce the same size, but with different. The third channel will be different.
okay. Let me ask this question a different way. Normally, the valid convolution, produces a smaller image size, right? Normally.
Yes.
So what happened here? That the convolution is producing the same size. So how was this done?
Padding was added.
How many?
How many padding? Padding
Yeah.
is f minus 1 over 2. In
F
order to
minus
get
1.
this over
Yeah,
2.
in this case, the padding, yeah, padding is equal to what? In this case, F is equal to?
I'm not saying it very well. I'm sorry. What is the value of f here?
Mhm.
I'm not saying the value of f.
The question is,
Yeah,
what is the value of padding? P. It is related to the filter size.
the filter size, yeah.
So how it is related to the filter size?
It's filter size minus 1 over 2.
Okay. Filter size is equal to what here?
I can see it well from the image.
You don't see it in the image? You don't see the
Yes.
filter size? Everyone doesn't see
Is
it?
it 3? No, maybe only me. It's a 3, I think.
Yeah, 3. So 3 minus 1 is 2 over 2. So this will be equal to 1, right? So the padding is 1. Okay. Why I'm asking this question? Because you have to know that. I mean, if you want to code your network, you have to know what you are going to do. That if you need your image size in the feature map to be equal to the input or the previous image, then you have to calculate the padding and the filter size based on the filter size. So you got all these. So let us finish this one. So we have the first convolution followed by another convolution with also a padding of 1, followed by a pooling. I guess it was a max pooling. It is max pooling, that's right, from here. Max pooling of, now we have pool 2, which is 112 by 112, which means that every 4 pixels will reduce to 1. And the memory in this case will be 112 by 112 times 64. We have 100K. Parameters are 0. Why is that?
Because pooling doesn't have parameters to train.
Pooling is not a learning layer. There is no learning whatsoever there, right? So the number of parameters will be 0. So these values will repeat, but with different sizes. Like here we have 64 filters. Here we have in the next convolutional layer, it is becoming more, 120, 128, then 256, then 512, but 3 layers here. And here 512, 3 layers. And final layer will have, so as you can see, the last image will have 7 by 7. So we start with 224. We reduced it at before the fully connected to 7 by 7. But how many? We have 512. So have you reduced the image that big to 224 to 7, but instead of 3 images, you have 512. Much deeper representation, much richer representation. You are extracting feature here. 7 by 7. That's it. You are converting an image of 224 to 7, just 7 pixels, but with very rich representation, 512. Then followed by our fully connected layer. We have 2 of them, 4096, 4096, and then Softmax at the end with 1000 because we have 1000 classes. And these are the parameters. Okay. So for VGG, most memory usage was in the convolutional layer. As you can see, it is very large. The pooling doesn't have that much storage, but most of the used memory is in the convolutional layers. And the parameters, most parameters are in the fully connected layers, as you can see here. If you compare these parameters with any of those, it is far higher than the convolutional layer. So this is why you have to be very attentive to the convolutional layer that you are going to use. So in this paper in 2014, so the architecture was mainly for this competition, and it was first. It has the first paper, the best results in localization. They use the same training procedure. Actually, one of the things that I didn't talk about, and I will not talk about, is how to train a convolutional neural network. It is. I'm going to actually post a very simple network and to show you how complex that is, how to train a network. Very simple one. They don't use in VGJ, they didn't use normalization. In Alex, they call it local response normalization, very special one. I will not talk about that in detail. They used VGG 16 and 19. So it showed that the 19 is slightly better because they have just extra layers. That's it. Still very expensive. Total memory is about 96 megabyte per image. Per image. Per training image, you need 96 megabyte. Then that's only for forward pass. If you for training, you need backward pass. You have to multiply this by 2, and total parameter is 138 million parameters. Now the language models has billions of parameters, but at that time, 2014, that was huge. Another architecture that was very successful too is called the inception models. It has a much deeper and more complex architecture. As you can see here, this is the input, and followed by this architecture. Here we have convolution, max pooling, normalization, convolution, normalization. Here, this is the inception model, max pooling, and then in parallel, as you can see, it has sort of many components in the same layer. Not just, as you can see here, it is only one component in the layer, but here it has, like here it has 3 components. One of them is max pooling, convolution. But if you look at the convolution, here it is 1 by 1, 1 by 1, 1 by 1. But here we have 3 by 3, 3 by 3, 1 by 1, and they are all concatenated to make one input here. Here concatenation, going to another inception layer, same architecture. And another layer, same thing. And here, it is becoming more complex. Here, augmenting and pooling, 1 by 1 convolution. Here, these are the same. These 2 layers are the same like here, but here we have something extra. This one, and it's actually is ending here. It is augmentation followed by convolution by one by one, fully connected, soft max result here. So it is producing something here, some real number, some sort of real number. And then it will repeat once again. This part is repeating again. And at the end, we have it here. This is the last inception module. And then we have fully connected softmax as this one. So not only it is getting deeper, but it is actually it is so it is the depth and the width both are getting bigger. So we have fully connected layers. We have convolution 1 by 1 times 1 plus 1. This is for the bias. And in the max pooling, we have 3 by 3 plus 1. And we have soft max activation. So this is architecture here, same architecture. So the main objective of the inception model is to focus more on the computational efficiency. As you can see, it is not as deeper as the BGG, right? But it is the width is bigger. So when you use this architecture with the competition, the error goes to 6.7%. It has 22 layers, counting the horizontal ones. Only 5 million parameters. In the VGG, it was 138 million. Here we have just 5 million parameters. So it is less than AlexNet by 12, by a factor of 12. It's 27 for VGG 16. The efficient module is very efficient. Doesn't have fully connected layers. Maybe just one at the end. They call this one, the first one that is attached to the input, called the STEM network. So the main objective is to aggressively reduce the input feature volume. So it has a convolution of 7 by 7, 64. So we have 64 filters, tried of 2, max pooling, followed by convolution 1 by 1, followed by convolution 3 by 3, and then max pooling. So that the input is reduced from 224 to 228 to 28 very, very fast at the input at the beginning. Here is this module with much better representation. So it is coming from a previous layer, going through in parallel, 1 by 1 convolution, 3 by 3 convolution, 5 by 5 convolutions, and 3 by 3 max pooling. Concatenate all these together and go to the next layer. So for using different filter size here, so you are actually doing what's called multi-scale featuring. You are extracting features on different levels. And the max pooling is doing some sort of summarization of your input. So you take features at different levels, take like a sort of summary, concatenate them together, and you get to the next layer. And this is the inception module. So it has what's called a local network. It is local because it has its own architecture. So it has an input, it has an output, but due to its local structure, it actually produces something that is much, much richer than the input. So we're going to diversify the learned features. Here we have two layers. we talked about the one by one fit convolution before, right? And it is used heavily in this inception module. All these are one by one. In one inception module, we have 1, 2, 3, 4 one by one filter. So the main objective of the one by one is to reduce the channel dimension. So we're going to summarize the number of channels into just one channel. So we talked about this slide before, that we have, let us say we have our input is of 64 channels. Our output is produced using one by one convolution with 32 filters. So we're going to have 32 channels at the end, but every one will be produced by one of 64. So every filter will apply 64 sort of processing, very similar to like averaging, but your average, like, is it here? No, it is not here. Yeah, it could be, we can use this one. So we have one by one, like here, one by one. Is this 64 for this particular pixel. Okay, let us just make it like this. These pixels will be produced to, let us say, this one here. One of the 32 will be here. So it is very similar as if you are actually applying the same fully connected layer on each input pixel. So every 64 pixels will be used to produce one of the 32 pixels. So as if you have 64 nodes producing 32. And the last one in this, actually Google LeanNet, also in 2014, Google LeanNet is using the inception module. So after the last convolutional layer, global average pooling layer is used to average across each feature map before the final convolutional layer, this one. So this extra layer that we have seen before at the side, actually they don't affect the output here, but they are just used auxiliary classification output to do what? To inject additional gradients at lower layers. As you can see here, this is the last one here is a softmax. So they try to in the middle of the architecture to see if they can actually reduce the error. So the error produced here, this is the loss, and it can be seen here and here. To see, so what's happening, that you are having gradient coming this way and from this area and from this area here. So you are injecting additional gradient at lower layers. They are afraid from the vanishing gradient problem, so they try to do that in the middle, get some sort of extra gradient. This is the reason we're having these what they call the auxiliary classification parts. So the Google LeNet has objective of deeper network with computational efficiency because of these parts. These are the results of the competition over the years. So it started 2010, and here it is recorded up to 2017. So first look at the human performance. The error is 5.1%. This is the best performance by humans. It started in 2010. And these are the different papers, the best papers in the competition. And the shallow network was just, the error was 28.2. 2011, it's becoming better, 25.8. Now starting to get the number of layers to get bigger, 2012, the error came down to 16.4. 2013, it came down to 11.7. And 2014, the layers came from 8 to 19. Now it started to become bigger. So the error came 7.3. Next year, 22 layers came to 6.7. And then there is an explosion of layers in 2015. So it goes from 22 layers to 152 layers. And the error came to, this is where, here it started to have actual neural convolution architecture. 2014, we have VGG. Google LeNet, but it was also in 2014. Then we have ResNet in 2015. Talk about that. The error came to almost half of the previous year, 3.6. 2016, it came down to 3. And CNET, it was halved by same number of layers to 2.3. And they are all convolutional layers. And as you can see here, this is a revolution of depth, and they all have beaten the human performance. So this is the challenge of depth. So we have the training error and testing error versus number of iteration, 10 to power 4, multiplied by 10 to power 4. So here is we have 56 layers and the 20 layers. And you can see that there's difference, huge difference in the training error between the two. So as you can see, the training error is with 56 layer is larger. This error is also larger. So supposedly it should be less, right? Because you are having more layers, then the reason for having more layers is that to get like what happened here, having more layers has produced less error. But here, this figure shows something different, that with more layers, you are having higher error. So this means that it is very challenging. In order to get the error lower than this, it is very challenging in terms of training. So you have to go back and check that the training tricks that we talked about last week. And then came because of the training problem, escape connection issue. That is, this guy was mentioning here. He said that there is a problem. The problem is that we don't train here because there is something in the gradient flow in the network. So the same guy here, the same paper, he said that, okay, let us make the deeper model emulate or simulate a shallow model, which means that we're going to copy from shallower layer uh, and set extra layers to identity. How to do that? So like in a shallow network, we have an input X, go to convolution, for example, and then apply ReLU, and then you get the output. And he said that, okay, let us do it this way. We have the same architecture, but from here, we're going to apply identity and get h of x. Identity means what? When we say identity here, means what? What is the meaning of identity here? There is no operation. I mean, h of x here is equal to the output here. Let us call it g of x. H of x equal to g of x. That's it. H of x is equal to g of x. So what is the objective of something like this? What does it? It does not change the output. The total output is still the same. But what is more it is adding here, if you think about it? If you're saying that h of x is equal to g of x, you are doing nothing. Computationally, you are doing nothing. You are just passing a function. But what is the objective here? So this learning identity function, change the network to learning identity function, which has no operation as extra layer is easy. So what is the function of doing that? Let us see. So this is the layer that we have. We have input x, convolution, radio function, convolution, we have an h of x. Here we are going to have the identity mapping. That is, as you can see here, we have same architecture, but we are going to have this connection, what's called the escape connection from the title, escape connection added to the output, this output. So h of x, this h of x will have f of x if this doing f of x. So we're going to have f of x plus x going as an output. So if f of x of 0, if there is a 0 here, there is no mapping here, h of x will be equal to x. So this is the identity. So you are adding the identity to the function itself. And this is what they call it residual, because f of x is the residual of h of x minus x. So this function, f of x, is equal to h of x now, which is h of x minus x, because we have this equation. And they call it the residual network, or residual component, or residual module. So what will happen when you do this? When you say that, okay, I'm going to add the input to the output. This is what you are really doing here. This is identity mapping. You are adding the input to the output. That's it. So what is the function we are doing here?
if we get information from the previous to the
طب let,
next state.
okay, let us go back to our computation graph. Remember that when we were calculating the gradient, this part, for this part, we have to calculate what? We have to calculate the local gradient, right? In order to have the downstream gradient that's going this way. We have a gradient coming this way. This is upstream gradient. Here we have the low stream gradient, and here we have the local gradient, right? So in this case, we here for this one, we have partial f, let us say partial x. This is our local gradient. But now we have what? We have partial h, partial x, which is partial f, partial x, plus partial x, partial x. Partial x is equal to
One.
yeah, it doesn't need any thinking. It should be 1. Now, what's happening is that if partial x is 0, right? You still have a gradient, partial h, partial x, which is equal to 1. So this means that if your gradient is becoming 0, you still have a gradient. If the gradient of the mapping is 0, you still have a gradient which is 1. So you are still keeping this network alive, and you can continue. And this is the main objective of having these skip connections. Then came the ResNet. This is what I call res for residual. This is where his name is coming from. That f of x, actually the actual function of this component is h of x minus x. So this is, as you can see, this is the ResNet convolutional architecture, as you can see here. But for every 2 layer of connection, there is an identity mapping. So this is the input followed by convolution, followed by pooling, 2 convolutional layers. But now the input is coming here, is added here. The input from this one is added here. All over the architecture, there is skip connection. So he, this Chinese guy, they have all these residual blocks, and every residual block has 2 3x3 convolution, 2 3x3 convolution, this one and this one. And it actually, according to this is, where is it? ResNet here. So periodically double number of filters and downsample, especially using stride of 2. Sometimes here we have /2. This is stride of 2. So we're going to double the number of filters. So as you can see here, we have 64 filters. Here we have 128 filters. So by having stride of 2, you are reducing the activation volume by half. And additional convolution layer at the beginning, at the stem. Here we have a convolutional layer. So if you want to go deeper, you can add a bottleneck layer. Like, so here we have 1x1 convolution, 3x3 convolution, and 1x1 convolution. So this is called the bottleneck layer. Starts with 1 by 1. So as you can see, it is 28 by 28, 25. This is the input size, 28 times 28 times 256. It's the same output. But in the middle, this layer, the bottleneck layer, is getting, of course, this size, or this is different from this one. It has some sort of feature extraction plus the input itself. So as if actually you can look at it as you have an image 28 by 28, as if actually you're calculating, let us say, the edges. The edges will be extracted here, and then you add it to the image at the end. So you are boosting the image. When you have the edges added to the image itself, you are boosting the image. This is what we call it in image processing. You are boosting the image. So this is what this bottleneck layer is doing. And they're still using the same concept of residual to improve the efficiency. So it is very similar to Google Linet. So these are some of the details. If you actually, if you have Torch installed, PyTorch, I mean, so import Torch from Torch Vision models, import ResNet. So ResNet, actually, this is one of the good things about PyTorch, that these famous models are part of the package itself. So you don't have to if you want to use it right away, you can do that. Just import them. And then the model is ResNet 18, and then you use the summary model 2, 3. This is input, device is CPU, and it actually will print out what each and every layer has. So conv 2-dimension 1, this is a size. These are the parameters, followed by batch normalization. These are the parameters, followed by ReLU. There is no parameters, and so on. So it will show you everything. So what is -1? This is if you look at this, this is a list in Python. What is -1 here?
It represents a number that we don't know the exact number of it.
And it depends on what?
On the other three numbers.
This one depends on the other three? Really?
No, I say that max bool 2D contains many numbers. The rest of these three numbers will be instead of -1.
Does it depend on the previous layer? It depends on the previous layer.
Okay, let us look at the first one. Let us look at the very first one. So this is, where is it? This is, so we have input, we have convolutional layer of 7 by 7, 64, straight 2. Is the same thing here? It is actually convolutional layer 64, and we have 112, 112. And here we have a -1. This is what? What is -1 here? What does it represent? You want to get the same. Is it from the input or it is in the middle? So we have a convolution followed by pooling, right? Followed by non-linearity, followed by pooling. So convolution, Bayes normalization, ReLU, max pooling, conv. So let's assume that this is the one coming after the inputs, right? We have a stride 2 here. So this means that the input is 2 to 4 times 2 to 4. So we have, since we have a stride of 2, then the output will be we have 64 filters, and we have input 7 by 7. I'm not sure that this is exact architecture or not. But anyways, let's go back to the -1. What is that? For the very first convolutional layer here, we have a -1. What is that? You need to be able to read the output of something like this and understand it. And number of parameters. So where this number of parameters coming from?
It's coming from the filter size and the input depths and the number of filters. Those are the weights.
So this 9408 is equal to what? It's coming from what?
9408 is the number of weights plus the number of eyes. The number of weights are the filter size multiplied by the number of filters multiplied by the depth of the input. Okay.
So this should be 64 times something, right? If you calculate this, it will be 147. So where is this coming from? 147.
Are those the number of filters, maybe?
Number of filters are here, 64.
So 147 is the size of the filter square times
square. There is no square that is actually starts with an 147. So 147 is a square. So what is the square root of 147? This is 26.7.
Okay, maybe the filter have a depth. It's not two-dimensional. Yes.
No, it is said that it is two convolutional 2D. Anyways, I'm going to leave this to you. Try to understand it exactly what's really happening with each and every number here. Okay, it's very easy to do. But as I said many times, it is very important to know all the numbers, where they are coming from, and what is, in particular, what this number 1 is, what does it represent. Okay. Okay, to train ResNet, something like this, they use batch normalization. After every, as you can see here, after every convolutional layer, there is batch normalization. They use severe initialization. They talked about maybe 2 weeks ago. The training protocol is stochastic gradient with momentum. Learning rate is 0.1 divided by 10 when validation error plateaus. We called that at the time, anyone remember the name? That is a learning rate decay. The mini batch size 256. With decay for regularization was, this is lambda that we used for regularization. They didn't use any dropout. So these are the parameters or the learning environment that you have used. You have to, when you train a network, you have to know what you're going to do. Now, this is the complexity of the different convolutional nets that were used in this competition. So here on the left-hand side is accuracy, top 1 accuracy. So as you can see, all AlexNet, batch normalization, AlexNet. There are other nets that I didn't talk about, like BNNet, NIN network, ENet. The rest are, we talked about the rest, ResNet, VGG 1619, ResNet 34. 34 is the number of, these numbers are the number of layers. 34, ResNet 50, ResNet 101, ResNet 152. And then the best two are the inception, V3 and V4. So these are the models and their accuracy. On the right-hand side, there are the accuracy versus the gigaflops, the complexity, how many gigaflops that is used. So VGG and CISC, which were very big, they have the highest complexity, as you can see, but not as accurate as the inception. So the colors are the same. In the two figures, the colors reflect the same network. So this one is this one. So it has highest accuracy and the complexity is not that big compared to the VGG. So you can see over why in G flops or G operations, gig operations here, because over the time, this actually also over the time, GPUs becoming much more efficient. So in order to have the same measure, you have to use the same unit, which is the number of operations. So this figure shows actually how you can have a very using a small number of flops, but you still get decent output. So you have to look at both. Don't look at one thing. Don't look at just here the accuracy. You need also to look at the cost, the money that you're going to pay in order to get this this accuracy. You can pay a lot of money for GG, but you still don't get the same accuracy. What they did, they found that the residual network is very successful. So they said that, okay, so why this guy, he said that why don't we make it wider, the residual net. So this is the basic residual net here, 3x3 convolution followed by 3x3 convolution, one filter. He said that we're going to repeat the filters here. Why not? So he said that it is the residuals are the important factor, not the depth. So he said that I'm going to go horizontal, not vertical. So he's going to he used F by K filters instead of F filters. So he repeated that. And he found that 50 layers wide ResNet network outperforms 150 layer of original ResNet. So if you have 50 layer wide of ResNet is better than just 150 layer network. So in this case, by increasing the width instead of depth, it will become more computationally efficient. So why? Because you have parallelization. If you have parallel branches, this means that you can parallelize. In this case, you can use more GPUs at the same time. There is also DenseNet. This came out in 2017. In DenseNet, each block, as you can see in the figure here, you have an input, convolution, concatenation of what? Of the input and the result of the convolution. The same idea of skip connection. And the input goes to every layer. As you can see here, it is here, coming here and here and here and here. So every layer is connecting to every other layer that's coming after. So this is going to reduce the vanishing gradient problem and strengthening the feature propagation, because you are using the convolved input and the input itself, both. And it was better than using 150 layer ResNet. This is architecture: input, convolution, dense block, convolution, pooling, convolution, dense block, and so on. So the problem with this architecture that they don't have, this is the main problem, they don't have a theoretical background. It is just like that we tried this architecture and it produces better results. And then they explain why the results are better, because that you are actually using the input to overcome the gradient problem. Then in 2022, this is very recent, came Conv Next. And before that, we have what's called the vision transformer. Transformer is, we'll talk about that when we talk about sequences, is the tool that is used today in language models for text processing. It is sequence to sequence. They used it, or a similar one, in computer vision. It's called vision transformer. Vision transformer, or called also Swin transformers, is the state of the art in computer vision. The question is, someone asked this question when actually the vision transformer came out. They said that, okay, now convolution neural nets are obsolete. They should not be used anymore in computer vision. These guys actually came with like a study about whether is it really true that we can get rid of convolution neural nets and use only vision transformer. So they used ResNet 50 and they re-implement the CNN network with better design. So what they showed that the Conv Next architecture has outperformed the vision transformer. So it is not dead. Though. So this, so what they did, they used ResNext. They used inverted bottleneck. This is the bottleneck that we used about before. Or is it? Yeah, this is a bottleneck layer, inverted one. Larger kernel size. Training strategy from 90 epochs to 300 epochs. They used Adam W optimizer, data augmentation like mix-up, cut mix, regularization schemes like label smoothing. They used very new techniques. This is what they call it next. And this is their architecture compared to the vision transformer. But anyways, I'm not going to get into the details of this one, but this just to say that people who say that we should not use convolutional network anymore, they are wrong. It depends on how you are going to design your convolutional network. And everything in this network is actually new. Changing the stage compute ratio, patchify, micro design ReLU will be GRU, fewer activation functions, fewer normalization layer. So they actually revolutionized the architecture. This is accuracy, this figure. There are different architectures here. Convnet actually outperformed the transformer. Convenext outperformed the transformer. But they consume more flops. You can actually use evolutionary algorithms like genetic algorithms, genetic programming to find the best architecture or to evolve the architecture. So you can use reinforcement learning and evolutionary learning to find the best architecture and prune over parameterized network, try to remove the parameters that are insignificant. So if you, this figure is coming from this blog about using evolutionary auto machine learning to discover the architecture of a neural network, or in this case, convolutional neural network, with the accuracy. Here, this one and this one, this one. So the main objective of this of this slide is that there is no particular architecture that will be the best. You have to try. There is no rule that says that this is the best architecture. So this is a continuation of the previous one. I'm not going to go through this, but okay. So far we talked about CNN, pooling, stacking, convolution, nonlinearities, and full connection. So we transfer from in computer vision, we have what's called feature engineering. We converted that into architecture engineering. There is a lot of details and tricks that we have used in CNN. What you should consider is the memory, the number of flops that we're going to use, how to reduce dimension, features diversity, parameters, and so on. Now, last thing before we take a break, transfer learning. So we're going to have a small data set, and we have large data set. Like ImageNet. ImageNet has huge number of images. So in transfer learning, this is what we do. The first step is that we train on a large scale data set. We create an architecture that is working with this large data set. Okay. Second step, we take this architecture and we take our data set, the small data set. We remove. So let us say in the ImageNet, we have 1,000 classes. We're going to remove this one, and we have the same architecture. We have just 10 classes. This is our data. It is 10 classes of, let us say, different cars, different types of car. We have our input image will be a car. The output will be what type, the model of these cars. Let us say that. ImageNet has images about everything. So we're going to replace the last layer with the fully connected for output nodes per our new category. And we're going to initialize this network, this part. Then we are going to update all parameters. First, we're going to freeze feature layer. All this will be frozen. This is our new architecture. These are frozen from the large scale domain. This will be frozen. This will not be trained. Only those will be trainable. The last layer weights could be layer or two, doesn't matter, but we're not going to retrain the whole thing. Only those parts will be trained. Like for example, this is trained on ImageNet. This will be actually trained on medical images. Different domain, but same features. This is the main reason. So we call this the source domain, and we call this the target domain. So what will happen if you train your original architecture with the images from, let us say that we have only here we have 100 images, that's it. You want to train these 100 images using because they are very complex. You cannot use a shallow network to build this application. So you have to use a very deep architecture like this one. But if you use 100 images with a deep architecture like this, it will do what? What is the problem here? You have 100 images, only 100 images, 100 medical images, X-rays, MRI, CT, anything. And you need to use a very deep architecture, like let us say ResNet 50. Can we do that or not? And why? This is the type of questions you get if you go to an interview and if you want to work in any place. And this is the questions you get in the quiz. So the main objective of the quiz is to know that you really understand the topic. You can hear me, right? I suppose. Can you hear me? Anyone? You are still there, right? So are you asleep or have gone away? So someone answer this question. You have a very deep architecture, and we have only 100 images.
Can we do augmentations?
No, will it work or not? What is the problem here? If you have a big architecture and you have 100 images, what will happen?
There will be overfitting. The
There will be
complex system would
overfitting.
memorize.
That's right. This is going to overfit. This is why, as you said, that we need to do augmentation. But instead of doing augmentation, we're going to do this transfer learning. We're going to get an architecture similar. The source architecture, source domain is similar to the target domain images that have been trained on huge number of images, and it is working. So what we're going to do, we're going to replace the last layer or the last two layer, it depends, and replace it, mainly the fully connected layer at the end, with the number of categories that we have in our target domain. Let us say that we are talking about medical images, that our classes are maybe different types of cancers, for example, 10 cancers. So here we have 10 output nodes. And our images will be images, let us say CT images for these 10 types of cancers, plus images about healthy people. So what we're going to do, we are going to freeze all, let us say, the convolutional layers. We're not going to change them, the parameters, I mean, but we're going to train the last two parameters. From the very last layer, the last pooling layer of the convolutional architecture to the fully connected layer. This will be only the trainable parameter. Will be very small number of parameters that will be trained. So our 100 images will be good enough to train this one, and we are not going to overfit. Okay. So, and this is as it says here, that we're going to freeze the feature layer. So this is the feature layer. Could be 50, could be 100, could be 1,000, doesn't matter. They'll all be frozen. And we're going to update only the last layer weights. These layer weights. So why is it going to work? Why people would think that this is going to work? Why is that? These are medical images, but ImageNet was trained on other images. Why this is going to work?
Because
What is
the
it?
frozen layers will have the low level features like edges and corners.
That's right. So these layers were able to extract features from the images that can be actually transferred to another image processing domain. Although the domain itself is different, but the features are the same or similar. So you still can use the features produced here to, this could be natural images, you can use them into medical images. So this is, it works extremely well. So feature learned from 1,000 object categories in ImageNet, work as well for new one that was not in the 1,000. It generalize across tasks. Object can be used also in object detection. as it's shown here. It doesn't always work well if the source data set, the big data set, is very different from the target data set. Then is not like satellite images. You are using your new data set is satellite images. So in this case, it might not work well because the features of satellite images are totally different from the features of the images that we use in ImageNet. And there is a paper about the same guy is doing a lot of work here that rethinking ImageNet pre-training. So this is effectiveness of more data. So as you have more data, you get better accuracy, but more complexity. I'm not going to go through this slide. Different domain. We have different low label settings in deep learning research. So these are the settings like semi-supervised learning, domain adaptation, domain generalization. Sometimes you call transfer learning domain adaptation, okay? Just to know in the name. There is also domain generalization, few shot training, unself-supervised learning. So we have the source, we have the target, and we have the type of shift that we have. So if we have single labeled, and semi-supervised means that you have data that are labeled. You are going to use this small data to label the rest of the data. And this is heavily used in medical imaging. In medical image, we have to have a radiologist to label the image, which is very expensive. So what they do, they hire a radiologist to tag or label some of the images and then use these tagged images to label the rest. So we have a single label. The target is single unlabeled. There is no shift type here. In transfer learning, we have single labeled and the target is single unlabeled. So we're going to use it to label that. There is no semantics. The semantics will appear in, like, look at this figures at the bottom of the slide. We have there is no semantic shift here. This is a bird. This is also a bird, but there is no semantic shift here. But here we have a clock, and we have like an axe here. So what is a semantic shift here? They are similar, but there is a semantic shift. What's that?
Content is different.
What's that?
The content is different.
The content is different, but there is a what it called that when we see that semantic shift, that there is just there is a semantics that have been shifted a little bit. So what is the shift here? You know what semantic is, right?
The meaning, or what
that's right.
human can understand.
So what is a shift here?
The time and the axe. I don't see any connection between them.
but there must, because you're going to use it, this will be the, let us say, the labeled one, and this is the unlabeled one. So we're going to label this one, and we're going to use the semantics here. Anyway, I'm going to leave it to you to research it out. Okay. Okay. So let us take a break. Let us take 10 minutes. So we come at the 50 minutes, 10 minutes from now. And then when we come back, we'll talk about the different architecture. We have said enough about CNN, and we talk about the sequencing. And this will take us to the recurrent neural network architecture. So let us take 10 minutes, and then when we come back, we'll talk about that. Okay. Okay, everyone, let us continue. Okay. Okay. So we'll talk about recurrent architecture. So far, we have been talking about architectures, whether it is feedforward or fully connected or convolutional. The inputs, our input data set, are totally independent from each other. So if we have a set of images, one image does not depend on the other images. There is no relationship between the images. Like this image has a car, next image is like a bird, and so on. There is no relationship between the two things. Okay. Now we're going to talk about a different domain, that there is a relationship between the input or the input elements, input samples. So we'll talk about the recurrent architecture. We'll talk about the basics of this and how to train them, and different gates that we use in the recurrent architecture, how to use them in text processing and computer vision. So let us start with this sequential data. So now we are going to shift to a type of data that it has a sequence. The sequence is very important. Like when you look at a sentence like this one, I took the dog for a walk this morning. It is very important to have the order of the words in that particular order. Doesn't make sense to change the order. It will have no meaning. So the order now is becoming an essential part of our data. It has to come like this. It applies to medical signals like the ECG or the EEG. The components or the sequence of components of the signal has particular significance. The same with the speech, the same, the video. The video is a uh, 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 very good example of the importance of a sequence. Like if we see the video is a set of images, a set of still images or fixed images, but they come one after the other. This is why we see it as a video. So the order of the images, of the frames, is very important. If you shuffle them, then it will make no sense. So how to model this sequential data is very, very important. So we assume that these data are coming from a certain distribution, data distribution, and they are. When let us look at uh, video frames. Let us say that we have 10 video frames, 10 images that make up a video. Then we say that these video frames or these images, 10 images, are coming from the same source, which has a same distribution. So it has a certain distribution. So what we need to calculate is the probability of having these 10 images together. What we call joint distribution. Sometimes we have we need to create. We have an image. We need to create a sequence of words to describe this image. What we call a caption. The thing that you see, the description of any image, is called a caption. So the caption, which contains M words, will also come from a certain distribution, and we need to calculate the probability of these M words given this bar means that given a certain image. And the same for recognition. Like we need to, given a certain images in a video frame, we need to calculate the probability of having a certain action like running or jumping or dancing or anything. So as you can see, we see three different types of calculating probabilities. The first one is calculating joint probability without having uh, any condition. The second one is calculating the probability of a certain sequence based on one input. In the third case, we need to calculate the probability of a certain value based on a sequence. So the sequence can be the needed output or could be the input. But in all cases, we are calculating probabilities. And this is why probability is a very important requirement in this course. You can also have, you can calculate the probability of a certain sequence based on another sequence. Like when we do speech recognition, our input is spoken, sorry, our input is a spoken sequence, which is x1, x2, like this one. This is x1, this is x2, this is x3, and so on. And the output is a sequence, like Hey Siri, for example. So the input is voice, is voice, actual audio voice. The output is a text. You can have an input as video frames, and the output is the action in each frame. Like a man is standing, a man is walking, a man is whatever. So this could be standing, walking, running, jumping, and so on. Still, we have the input as a sequence, the output is also a sequence. Before, we have inputs as a sequence, and we're just calculating the probability that's coming from a certain distribution. But here we have the input as uh, 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 one input, and the output is a sequence. Here we have the input is a sequence, output is one value. The input is here the input is a sequence, output is a sequence, and same here. And in all cases, we're calculating probability. We can have a video as an input, and the output will be a description of this video as words. Or we can have a sequence of words in a certain language, and the output will be words from another language. They don't have to be of the same length, right? N and M. So then can have N words in English. This will be translated to M words in Arabic, for example. They don't have to be of the same length. So these are the challenges. That's first, that we have a variable length sequence. They don't uh, they don't have the same length. The input, actually, if you are building a model that will translate sentences in English, let us say to French, I mean, the length of the sentences will not be the same. Like this slide, it has 4 sentences. They are not of the same length. So this is the first problem that we have to deal with variable length sequences. And at the same time, we have to maintain the sequence order that, like here, I took the dog for a walk this morning, that we have to keep the sequence as it is, cannot change. We cannot shuffle the words, or we are going to lose the meaning. And we have to keep track of long-term dependencies, which means that, let me go back here too, that let us say that this word was like, we need to complete this word. It was not, it was missing. So we give the network like the previous words, like I took the dog for a walk. This, we need the network to complete this. So this is can be called long-term dependencies if it is very far away. If the statement is too long, and we need, like, say that you're talking about, you have a paragraph, actually you're describing that maybe you have visited France. At the beginning, you say that I was visiting France, and you keep talking about France, and then at the end you remember that you say that, yeah, and French people are speaking, it should be French. So French will depend on very few words that appeared in the beginning that you visited France. So this was called long-term dependencies. And this is a big problem in a sequence processing. The other thing is that we need to share parameters across the sequence. We have shared parameters before. In which architecture? We have only two architectures. We have the fully connected network and we have the convolutional neural network. In which parameters we share parameters? In which architecture we share parameters among inputs? And why?
CNN.
Why? That's right. It is CNN. We share parameters in CNN. Why it is sharing parameters? Or where
And
is this
because of the
happening?
filter.
Because the filter, actually, we
Oh,
have the image like this, and the filter, which is 3 by 3, for example, scans the image like this, right, left to right, top to bottom, and every 3 by 3 window of the image is actually sharing the same 9 parameters of our kernel, and this is where the sharing is happening. We're going to do the same with the recurrent architecture, and we're going to in a different way. So this is the basic difference between a fully connected layer and a recurrent layer. So a fully connected layer, we have our input and input layer going to a hidden layer, going to an output layer. All these are vectors, as you can see. In the recurrent layer, we're going to uh, have the hidden layer using its previous time t, time t or the nth time. It is going to use the output from itself in the previous step. So we have at step 10, the output from the hidden layer at time 10 is dependent on the current input xn at time n plus hn minus 1, h at time n minus 1. And this is where the recurrence is happening. That recurrence in general, when we have like an nth, the, the output, let us call it uh, uh, a at time n, is a function of a at time n minus 1 or n minus I. Doesn't matter, it has to be 1, but any previous time, maybe plus other things. But it depends on previous values of itself. This is where the recurrence is happening. So what we're going to do, we're going to unroll this architecture in time. Unroll means that we're going to have to draw the same network, but at different instances. So at time t equal 1, the first time, we are going to have input x1 producing output h1, producing hidden layer h1, producing output y1. At time 2, when we input the second, let us say second word, we have the same architecture. We have input x2, we have output h2 from the hidden layer, but h2 is taking also another input from h1, previous hidden state, to produce y2. y3 is using input x3 and using previous h2 to produce y3. It is the same network, but unrolled in time or unfolded in time. So when you see this, don't think that we have three different networks, the same networks, but it is, we are just here. This is our time axis, the network at different time steps. We normally have from h1, we have h naught coming to h1, but initially it is always 0. So we have different recurrent architectures. The first one is vanilla neural network, the regular neural network, the conventional neural network, in which we have the feed forward, one-to-one. So we have one input and we have one output. Every input has its own output. There is no dependence whatsoever. And this is called the one-to-one network, one input to one output. The next one is that we can have one-to-many. We can have one input that will produce many outputs. Like the input can be an image, and the output will be a description of this image, a caption to this image. So in this case, we have the input is one image, the output is a sequence of words. And this is one-to-many. And this sequence of words depends on each other. So it has to be, as you can see here, the first output will have an effect of the second output, and the second will have effect on the third output. Or we can have many to one. Like we can have many inputs and the output will be one, like action prediction, like we have different images in a video, and the output will be just one action that a person is talking. Action here is talking, just one output. So we're going to have three inputs, for example. We have many inputs here. So the first input will affect the second output. The second output will affect the third output, and so on. And this is many to one. We have many to many. So the input can be of many inputs. The output will be also, or many items. The output will be many items. Like video captioning, you can have a description of every video, every frame, right? Every frame has, like in the first frame, man is talking. Second frame, man is uh, waving. Third frame, man is smiling, and so on. And as you can see, it is a little bit delayed. It has to wait just uh, to produce the output. And this is actually also happening in machine translation. When we translate from one language to the other, we have to wait for maybe 2-3 words before we start translating. They don't translate. If you ever listen to any uh, uh, translator, they have to wait. They don't produce output right away. We have also many to many, but instantaneously. I mean, for every input, we have an output. So like a video, in the first video, uh, uh, it can have a certain output. So video classification, like this video has a car. This video has the second frame. It has a plane. Third frame, it has a ship, and so on. So it could be a frame about items, and every video frame can be classified to the corresponding object inside this frame. Okay, so we are going to focus more on text, okay? Natural language processing or natural language understanding. But let us do processing first. It is much easier than understanding. So remember that we are dealing with computers. So everything has to be transferred into numbers. The text has to be transferred into numbers. So in traditional natural language processing, we have our words like each like here we have hotel, conference, motel. They're all, each one has its own representation. So what's happening is that what we called before, we're going to represent the symbols here will be one hot encoded vectors. Let us say that in here we have our dictionary is 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 15 words. That's it. Our applications only has 15 words. So if the word if we're writing a sentence and the word and the sentence contains this word, then it will be one. Otherwise, it will be zero. We're going to have the 15 words. If the word exists in that sequence, so this is the first word, this is the last word in the 15 words. If the word exists in the sentence, it will have an one. If not, it will be a zero. So, for example, the word motel will have the one here, and the rest will be zeros because it is only representing the motel. And hotel actually is another representation, like here. So, if the word exists uh, uh, in the sentence, we have its corresponding position will be one. And every word has this 15 binary bit representation with only one word, one bit at a time being set according to the location of the word. This is why they call it localist representation. It depends on the location of the word in this representation. Uh, this is what's called one hot encoding. So our input will be of 15 bits, as you can see. This is the first representation. But as you see here, we have two words like hotel and hotel. They're very much common, right? They're similar. A motel, the hotel is a bigger version of the motel. Like the motel is just rooms, that's it. But the hotel is rooms and some facilities like conference rooms, ballrooms. Sometimes there is a gym and a pool, and so it is much bigger than a motel. But they are very similar in their function as a guest house. So in their representation, they should be very close to each other. But in this one hot encoding, this correlation between the words does not exist. They're totally different. Like if you have, like let us say we have a man and a woman, they should be very close because they have the same origin. If you have like a car and a bicycle, they should be close in their representation. A boy and a girl, they should be very close. A boy should be close to a man, and the girl should be close to a woman, for example. So it is very important to have this sort of representation in which words, the semantics are close. And this is what's called, we do a vector representation of the words. So a number of words in the vocabulary, if we have huge number of words, then we cannot have this representation. This hot encoding will be totally impractical. We have to have a different representation. So for every word, we are going to create a dense vector for each word, like a vector like this. So like a word jacket will be of this maybe 10 dimensions. As you can see, positive or negative values, they represent the word jacket. But those dense vectors will be chosen so that it is similar to vectors of words that appear in similar context. Like jacket is close to coat, close to sweater, and so on. So in their representation in these 10 dimensions, they should have very close values. And if you calculate the length of this vector, the length of this jacket, we write actually normally like this, jacket. It should be 1. How we calculate the length of a vector? Anyone? Let's say that we have a vector, just 2 dimensions, A and B. What is the length of this vector? Let us call it. How to do that? What is the length of the vector A? I didn't hear that.
Root
I
A
can
squared plus B squared.
exactly. A squared plus B squared under the square root, right? And the length of the jacket here, if you square all these values, 10 dimensions, and take the square root, it should be equal to 1. So the length of the vector should be equal to 1. If we want to measure that, the representation of coat, let us say coat. It has another 10 dimensions. We need, if we want to check whether they are both close to each other in this representation or not, we calculate the similarity. How we calculate the similarity between the jacket and the coat is by calculating what?
Cosine similarity A dot jacket
The
dot
cosine
coat.
similarity, exactly. So we get the length of the jacket times the length of the coat cosine the that angle between them. Since the length is 1, the length is 1, so the similarity will be the cosine, the angle between them. We know from vector analysis that if two vectors are so close together, their angle will be close to 0. As they go away, one go away from the other, the angle will increase, then this means that the similarity is not that big, right? So we measure the similarity by getting the angle, the cosine, the angle between these two vectors. The way we convert a word like jacket into this representation is called embedding or word representation. And this is a very famous layer in any platform like PyTorch or TensorFlow. It is called actually embedding, a layer called embedding. When we have fully connected, we have embedding layer. And this is the first layer that comes after the input. So we have the input as words, and then we go to embedding. There are different way of embeddings. I don't know. It is not here. Okay. Different way of doing embeddings, like bag of words, like glove. I'm not going to talk about these techniques. If you take any natural language processing course, they will talk about that in details. Glove and others. So at the end, the basic objective is to convert every word into a dense word, like a vector, and it will be very close to similar words. Like man and women will be very close to each other. King and the queen will be very close to each other, and so on. So how can we model a language? This is a very important thing that we see on when you try like any AI tool that you are using most of the time now is based on language modeling. So it is many to many. First thing, it is the type of sequence that we are processing here is many to many. Let us say language model, we translate from English to French. So the input is a statement in English, the output is a statement in French. Or in the language model, it actually will produce the outputs, like it will predict the next output. Like the input here is start. We have a start symbol. We need to tell the model that we are starting now. So the first input will be start. These are not parallel inputs, okay? These are inputs are entered one at a time. So this is at a time 1, time 2, time 3, time 4, time 5, and so on, okay? So these are not parallel. This is one word at a time. Like we start, and the language model will produce an output right away. Like, oh, this is after training, of course, like that. And they are going to use that as an input next time to produce a second word, brown. And we're going to use brown as a third input to produce cow. And cow will be used an input to produce jumped and so on. This is what actually you see on when you use like ChatGPT or Gemini or anything of these tools. So first we have to use,
Doctor,
yeah,
sorry, I have a question. If one word was predicted wrong, this would affect
yeah.
all the
This is
upcoming segments.
that is what they call it in language modeling, hallucination, right? It can you actually you can see that you can get very strange output sometimes when one word is wrong. We'll talk about that. We'll talk about how actually this is happening. So don't jump the gun here, as they say. We can just wait. Okay. So here the red ones are the word representation can be v-dimensional. One can be one hot encoding or dense vector, whatever. Outputs are the classification of over v dimensions, could be softmax. So what's happening here is that any of these words, remember that when I talked at the beginning about the probability of the output, this is the probability. The is having the highest probability of all the words that we have in the dictionary to be produced here. The word that. And this is why it is predicted here as the. Sometimes you can have the has a probability of point 315, and there is another word that is 0.31554. This is the correct word, the, and this is the correct word. This is another word which is very close to the. It could be let us see, and what's happening, our model will pick the word with the highest probability, and this is higher at the fourth digit, but still for the computer it is higher. So what will happen? It will pick the word "and." So "and" will be followed by a brown, so it is not correct from the linguistic point of view. But this is where the hallucination happens. Just one word, which is just very close to the correct word, but has a little bit higher probability, just a slight higher probability, and it will be picked up. Actually, this problem has been solved in different techniques, but this is what's really happening. So how can we model the language? Any language. So we are going to use many to many. Okay. So we have our recurrent architecture. We have our input X at time t, and here we have recurrent in the hidden layer. It is a recurrent, which means that uh, the output from one time step will be used for the next time step. And then we have an output here, Y. So Y depends only on the hidden layer output. The only thing that depends on itself is the hidden layer output. That's it. This is the only part of the network that depends on itself. The output depends only on the hidden layer output. So the output is static in terms of the hidden layer output. So the hidden layer or the recurrent architecture in the hidden layer has an internal state that will be updated as a sequence is processed. Every time this output of the hidden layer will be updated based on the sequence that it is receiving. So at time tx, at time 1, we have an input x1. It will produce an output h1. and output y1. Sorry, hidden layer h1, hidden state h1, and output y1. At time t2, we input the second symbol x2 after, of course, after embedding now. So we assume that these x's are embedded. This is a word representation. And the hidden layer will produce h2, which goes to the output to produce y2. And also will be used for time step 3 when we input the third input, and it will use to produce h3, it will use the input x3 and the previous hidden state h2 to produce y3, and so on up to x at time t. At time t, it receives the input xt after embedding, and then we'll use the hidden state ht minus 1 to produce ht to produce final output yt. So in this case, this is unrolled recurrent architecture. So for every input, there is an output, like we have seen here. Every input has an output. Every input has an output. This is many to many. So how are we going to update what are the equations? At the end, we have to have equations. So we say that the ht at time t is function which depends on weights w, which is here, of the input, the current input xt, and the previous hidden state ht minus 1. This is all the state. And f is a function. It could be like sigmoid, hyperbolic tan, ReLU, any function. That's it. In the feed-forward network, if you remember, that was not existing. ht is function of xt. That's it. The hidden layer, output of the hidden layer depends on the input, and we apply a certain function that is also dependent on the weights connecting x to h. The same thing here in recurrent architecture, except that the input to this f is concatenation of the input and the previous hidden state. The output here is another function, depends on a matrix from h to y, and depends only on ht. So y at time t depends only on ht. There is no recurrence. So at time t1, the recurrent architecture, the hidden layer receive an input from x1 and h0, which is normally 0 at the beginning, and to produce y1. And at time 2, the network received an input x2. It's the same network, okay? It is the same. So here we have weight w. It is the same weight. This is why we call sharing at the beginning. We are sharing the same weights among time steps. So let us call this one WXH. This one is WHY. These weight matrices are fixed, or sorry, are shared between time steps. And at time t3, we use h2 from the previous time steps, and with the input x3 to produce h3 that will be used to provide y3, and so on up to the time t, where ht is produced using xt and using ht at time -1 to produce yt. And this slide is talking about this sharing thing, that the same function and the same set of parameters are used every time step. Same function f, and the same parameters w, h, x, h will be used at every time step. So this is where the sharing is happening. And ht depends on xt and ht -1. This is where the recurrence is happening. And we apply a function of f with parameters w's. So let us be more specific. Let us say that this fw will be converted to this. ht will be, we're doing this transformation. Remember that it is in the feed-forward network, it is input xt multiplied by the weight matrix from x to h. But here we're going to add another matrix, whh. Here we have matrix wxh. So xh will be multiplied by xt, and whh will be multiplied by ht -1. And then we apply our nonlinear function, the hyperbolic 10. This is the f. And the w's are this w plus this w to produce ht. The output is only dependent on ht, so there is no recurrence in the output. So y at time t is w hy multiplied by ht. And this is called the vanilla RNN. And it was introduced by a guy called Ellman in the 80s. It was, at the time, it's called Ellman network. And this was the very first neural network, first recurrent neural architecture that was proposed in the 80s, as you can see here. So we need to learn this one, and this one. As any other neural network, these weight matrices need to be learned. I'll take here we are going to talk about an example, and then I will end it here. Okay, sentiment classification. Like when you write a review about a book, a restaurant, a service that you have taken in any place, you go to the website and then you write a review. Could be positive, could be negative. So you can classify a restaurant review from Yelp or movie from IMDb or anything. At any case, it is positive or negative. So what type of recurrent network we are using here? Is it one-to-one, one to many to one, many to many?
Many to one.
Many to one.
Many to one, exactly. So we have many. Our input is multiple words and one or more sentences, could be a paragraph. The output is just one thing. One is either zero or one. One is positive, zero is negative, for example. So this is many to one. So for example, you can say that the food was really good. As you can see, it is a statement of 1, 2, 3, 4, 5 words. Or you can say that chicken crossed the road because it was uncooked. So this is positive, and this is negative because very sarcastic. That is actually, it says that the customer here is saying that chicken was not actually cooked well. So he said that the chicken crossed the road because it was uncooked. Anyways, so So here we have five words. Here we have more than maybe 8 or 9 words. So it is variable length. As you can see, the input is variable length. So there is no point to have a fixed length input as we do in fully connected network. Like an image, if we have an image of 10 by 10, we're going to have 100 nodes as an input. It is fixed. But now our input is not fixed anymore. So this is why we use the time to reflect the different words. So every word will be converted into word representation, like either hot encoding or dense encoding, whatever. But now every word will have its own representation, and all of them, the representation is fixed now. The embedding is fixed. But in order to take the sequence into consideration, we do the recurrence. So we have this input that going to the hidden layer. In order to link the food with that, we're going to use the representation. Look at the hidden layer representation as if it is some sort of representation of the word. So the output of the hidden layer, the first time, each one will have some sort of representation about the word the. The second word, when you enter food, in order to make food somehow related to the, you use the representation of the with to produce the H2, which will represent what? Will represent the food, the two words. H2 at this time will represent the two words, the food. When you enter the third word, which is H3, which is using is as an input and using H2 also. H2 is representing the food. So H3 will represent the food is. As you process or keep processing the input, every hidden state will represent all the previous words. So this way you are keeping the sequence, or you have some sort of representation in the hidden layer that actually has the context of the words kept in order to produce output. Like here, this is the representation, right? Yeah. So we have that will produce H1. There is no output. The output here, actually, the output does exist. There is a Y here, but it is ignored. We don't need it at this time. We don't need the output at this time. But it does exist in the network. And then you enter the second word food to produce H2. There is no output, or the output is ignored. You produce, keep entering your words till you get to the word good, the last one. And only then you get the output. And you can use, let's say, linear classifier to say that it is good or bad. All the outputs that was here, and here, they were ignored. We had an output, but you can ignore it till you reach the last one. When you enter the last word, then you enter your actually, if you are training, you enter the output will have a value of, let us say, 1 to say that it is a positive feedback, and you keep training. We'll talk about training later, but this is what's happening in testing. So you can ignore the output for time 1 and time 2, but you keep it for last time. So I'll stop here at 34, and next time on Wednesday we will continue this. Note that because you have a quiz on Wednesday, so we are going to have half a lecture, and that will start 1 hour and a half of our regular time. I updated the meeting We're going to start at what's the time now in Cairo? It is what?
6:41. It's
Yeah,
6:41.
5. So we're going to start at 6 or 40 or 5.
It's 6:41.
Okay. So we're going to start at 5:30, I guess. Okay, that's on Wednesday. Any question?
Doctor, yes,
Yeah.
I'm a little confused about what have you said. The quiz would be in the lecture or what?
No, it is. I think it is. Dr. Mona told me that it
It's
should
12
be.
p.m.
No. Just a second. The quiz. Let me open on Q because she told me that it will be 10 about 10 a.m. actually Cairo time.
Yes, exactly, 10:30. My bad.
Right? Just 10. Okay.
Mm.
So you cannot have more than 3 hours for a certain. I mean, according to Queen's regulation, you cannot have more than 3 hours for a certain subject in a day. So you have we're going to have 90 minutes for the quiz and another 90 minutes for the lecture.
Okay, thank you, doctor.
Okay. Any more questions? Okay, guys. See you on Wednesday.